originally when I kind of first thought of it, but I was kind of in my head thinking it was going to be to like a kind of class-sized group of about 20, 30 people. And last week I was told that I was expecting about 160. I can see I've got slightly more than half of that. So that's better attendance than I've been getting in a lot of my team sessions in the last few weeks and months anyway. So, but I'm going to go with what I've planned, which is slightly different from what I originally had, but there will be time for discussion, but I'll use breakout rooms for that just to kind of keep it manageable. So if you don't mind, I'm going to ask you just now just to keep your mics and stuff off, but there'll be an opportunity for you to kind of work in a wee team later and hopefully share what you come up with in your chat. So today's discussion group, it will be short, and I'll definitely make sure you're finishing time for your lunch, although you can't get it from the Stirling canteen this year. So I'm just going to talk a wee bit about using DESMOS, particularly with National 5 and higher maths classes. One thing I've done in my teaching a lot in recent years is use DESMOS just to make it really quick and easy to link a lot of the work we do when we're doing questions, particularly in the relationships unit of National 5 and also in the higher maths course, to make pupils try and see the link between the algebra that we're working in the classroom and what it looks like in a graphical sense, just to try and encourage them to see that the two are the same thing and how they work. So in this session, there'll be kind of three main parts to it. I'll show you some of the stuff that's available on DESMOS already made. I'll show you how to make your own kind of resources on the graphical calculator. And I'll get you in a wee small group to create a graph or a kind of, that you might use in some way with a National 5 class, just to kind of get you doing it. Because I think if you do it right away, hopefully you'll kind of remember how to do it for longer and be confident taking it into your own teaching. It won't be a chance to debate about which is better, DESMOS, GeoGebra. I know from previous conferences, anytime one of these is mentioned, it's sometimes there's a tendency to descend into an argument about which people prefer. If you're using one of those other pieces of software and you're happy using it, keep doing that. I'm not trying to tell anyone that they should use DESMOS instead of something else. But DESMOS is what I tend to use. It's what I know. So obviously that's what I'm going to talk about today. Sure, it's what you signed up for. If you wanted to do find out about autograph, go to a course on autograph. But I'm not knocking those pieces of software at all. I think they're great as well. Also, DESMOS has other functionality outside of the graphical calculator. And if you're interested in how to access some of those kind of teaching resources, there is a session this afternoon on that as well. I'm going to be focusing on the graphical calculator aspect of DESMOS in this session. Okay, so that's what's going on there. So what I'm going to do today, first of all, is just kind of take you and show you a couple of things on the graphical calculator. I've got a few examples here. I'll share these slides so people can get links to them later, but really they're quite easy to access yourself. So if you go to DESMOS, this is the screen you will get when you kind of arrive at DESMOS. And I've deliberately not logged in just now because I want to show you what's there independent of anything I've created myself. If you didn't already, it's very quick and easy to sign up for a DESMOS account. And for what we're doing today, I would recommend having done that. But if you haven't, you'll still have access to the kind of first things I show. You don't need your pupils to have an account to access anything unless you're asking them to create graphs and then go on to share them with you, which might be something you want to do. But for what I'm showing you today, it wouldn't be necessary. Down here are the kind of extra resources that I was referred to in my previous slide. But as I said, folks, that's maybe more for the other session this afternoon that I mentioned that someone else is running. What I'm going to look at with you is the graphing calculator. So if I go into here, you get a very basic graphical calculator here, and some of you may have seen that. You start with an untitled graph here, and you can just type a function in there if you want. You can type a coordinate. So you could plot the point 1, 4, oops, that's not 4, and show where it goes, 1, 4. And you can maybe draw a graph, let's say a straight line graph. Let's go one that says y equals rather than x equals, so that we're working on the xy plane. And you can get this graph quickly and easily. If you're working in school, you might find it helpful sometimes to put it in projector mode like that. If you just go up there, you can change various settings in here. That's quite handy to do. If you're working with trig, toggling between radians and degrees is helpful. And you can change the scale of your axis, and what's labelled and what's not labelled as you like there. And you can zoom in and out here or using the mouse wheel. But what I want to show you is, before we start kind of creating things on DESMOS, is there's a great bank of resources already in existence in DESMOS if you go into there. So just to show you that again, if you click these 4 lines in the top left of the browser when you're in DESMOS in this mode, you can create and see the graphs that DESMOS already has. And one you might use with the class is if you click on this one, line slope intercept form. This is definitely quite a handy graph you might use when teaching straight line in a National 5 class. So when you're doing that kind of part of the relationships unit where you look at linear graphs, you can show here the properties of gradient and how they affect the line. You can talk about zero gradient matching with the horizontal line. You can talk about negative gradient for sloping down. It shows that quite nicely. You can animate it. You could even perhaps have that up for a class animated as a prompt and talk about, you know, what's changing here, why is it changing, what do you notice. It's up to you. You could use it to introduce the topic. You could use it to revise the topic with the class as a kind of prompt for discussion. It's entirely up to you. There's all kinds of ways you could use this. And that will maybe depend on what technology you're using and have. And of course, you can show the y-intercept here. It is interesting with animations like this, I find sometimes, is that obviously when we talk about changing the value of b here, we would be thinking about that as a vertical shift. But actually, when you animate that, I think a lot of the people would actually see that as a movement up to the left. So just something to be aware of. Some of these things, sometimes when you have an idea that, oh, I'll show them that, and they'll see that that means go up and down. Well, actually, for this particular graph, at first glance, it maybe doesn't look like it's going up and down as I change the value of b there. But you can maybe show that it is. You know, if you actually click on that, you can show that the y-intercept actually does correspond with the value of b for this particular graph. So that's just one example of a graph I might use at various points when teaching straight line graphs, particularly in that form to a National 5 class. Another one I used this year, I don't have a National 5 class this year, but I have a higher class. And one I showed them is this, the inverse of a function that comes as standard in that bank there. And I really like this one, the way DESMOS has created it. It's really quite neat the way it shows it. You can change the function up here. They've started with a kind of a quintic function polynomial here, and they've kind of generated this way of getting the inverse function. Now, there's a lot to talk about here, but what I kind of drew the attention to my higher class was that for the red points compared to the black points, was to notice that over here, what had happened was that the x values and the y values had swapped places, that I had interchanged. So A was the x coordinates on the black curve when I plot these points, but that's then the y coordinate on the red curve. And f of A, so kind of what I get when I substitute A into this function, was the y coordinate of the black curve. That becomes the x coordinate of the red curve. And I kind of used that to really reiterate what I'd said in class, what we kind of put in our notes about when you use the inverse function, the domain and range swap. You know, what was the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the function. Obviously, I'd already introduced concepts of domain and range, but I was really keen to keep talking about them as much as I could to kind of get that idea across about domain and range. But what's nice, of course, is that that idea of the domain and range swapping, which you've talked about, is then very visually shown here as that reflection in the line y equals x. So rather than those being kind of two distinct concepts that the higher class have to learn, that when you find the inverse function, the domain and range swap, and the reflection of the original graph of f of x in the line y equals x is the inverse function, they're not two different things. We're showing here that they're actually the same thing. And it's just a nice way to do that. And you can change the function up here and it still works quite nicely. You might think, do you know, I'm actually going to start with something a bit more basic. F of x is x cubed is maybe a more basic function to show this as. And you could even just say, well, what do you think the y equals version of the red function is? And hopefully starting with a kind of one-step function, they'd be quite confident about coming up with the cube root, which I think I will find in here. Yeah, there's the cube root of x. And you can confirm that that overlaps the function there. And you can kind of, then scale it up a wee bit and do, okay, well, what about if I make it a two-step function, like +5, and then you can show, well, actually, take away 5 there doesn't work. And then, that then maybe leads to your whole algebraic method of, okay, well, it needs to be the cube root of x minus 5 inside. And you can show that your algebraic methods for finding the inverse function actually work and relate to this whole idea of the graph, rather than it being separate, distinct facts about inverse functions, by kind of having the graph there alongside to refer to. You're just kind of putting the two things together. It's definitely something I've really tried to work on in the last few years. It's just letting them see that the graph is the same as the algebra they're doing. It shows what they've been doing. It's not, oh, this is a graph question. So much of what we're teaching in National 5 relationships and in higher is the graph. Even when you don't have to draw a graph, there's a kind of graph connected to it. So that's one I've used recently. Another one I used with my higher class, I actually taught this topic first, sketching the derived function, and then to revise it, I just put this graph up as a prompt one day, and sort of said, what does this show? And, as a kind of revision task. So this is the one called calculus derivatives in the bank there. And it's quite unusual because certainly when I teach my higher class sketching the derived function, I tend to teach them to draw them on two separate diagrams. So if they had the original function, which is the red curve here, they would draw the derived function on a separate graph directly below, where I'd have the kind of x-axis lined up and the kind of root, the stationary points of the original function would become the roots. So it's quite unusual for them to then see it all on the same graph, but it leads to really kind of good discussion. So at first they probably say, well, we've got a parabola and another polynomial. They might know it's a cubic. And we talk about what they kind of know. And then to kind of prompt a bit more, I might then just kind of select certain key points on the graph and see if they notice anything, see if they notice the x coordinates are the same for those. I might change the function to make those maybe integer values, just to kind of keep the values smaller. I mean, again, this has got that kind of functionality where you can animate it to kind of show how the graph's affected by different changes, which is quite nice. But you could also just type in a function you want here. Certainly, what I did was I then returned to this when I wanted to teach the fact that the derivative of sine x was cos x. So I put that in there. I kind of had different functions up there. We talked about, firstly, kind of, if I differentiate a cubic, so I'd maybe have, first of all, I've put the cubic in there, the standard cubic, bx squared plus cx plus d. And if they don't have sliders, add them in and kind of just muck around, show them no matter what I change those values to, as long as a is non-zero, then I get a parabola. So the derivative of a cubic is always a parabola. And you can kind of, then dive in and say, okay, well, look at this. What's the derivative of sine x? And hopefully they would recognize that as the graph of cos x. Obviously, I'm in radians here. And yeah, and it's nice. You can then refer to this. Well, look, DESMOS is using that notation that we use, the derivative with respect to x of f of x, is what the second function is. And it's just relating those two all the time, This is what the graph of that looks like. This is what we would write, when we're working, and just trying to keep the two together. And I find DESMOS kind of allows me to do that really quickly and easily with classes. And there is that kind of great bank of resources there. And quite often what I'll do, depending how I'm doing the lesson, I might just show it on the board. If the pupils have access to technology, such as iPads or Chromebooks, then I might be emailing them a link. And it's very easy to do that. I think I did that in my slides, but like if I pick one of those there, if I go to that line slope form, if you just go up here and copy and paste that URL, it will take whoever has, sorry, I've got my own toolbar up here that's blocking me do that just now. Let me just move that down. There we go. If I kind of copy, I should be able to then kind of paste that into our chat. And anyone who has access to that chat will be able to, there we go, chat. So if I put that in there, you should be able to click on that and you go straight to that page. And it's as simple as just copying and pasting like that. So I can copy and paste that into an email to pupils, into Teams, into Google Classroom, whatever it is, you know, that you use to share things like that. You probably don't want to put it on the board and ask them to type it in, but copying and pasting is a pretty quick and easy way I find to kind of share these with pupils. But what I really want to show you to do today, I wanted to kind of let you know that that's all in there. But what I wanted to also show you is that you can create these yourself. And if you have a login, and I think instructions were sent out for you to do that, but if they weren't, don't worry, you can kind of do it yourself. You can create your own. And I have a whole kind of number that I've created here in recent times that's sort of saved in my own library that gets saved up here. So here's one. I was teaching closed intervals remotely to my higher class in the last few weeks. And we'd done stationary points before. And what I did as a kind of prompt during my live lesson was I gave them this function and asked them to find the maximum value in this given interval. Now, they'd never had a question presented like that before. I hadn't taught closed intervals, but I had taught stationary points. So when they saw the words maximum, minimum values, the majority of pupils in the class kind of thought stationary points. So off they went and they found the stationary points and they told me that the maximum value of the function was 10 and the minimum value of the function was 8, I think. No, sorry, 4. And so I said, okay, well, that's really interesting. And I'm seeing loads and loads of good work there. They sent me kind of photos and I was seeing their kind of nature tables, their differentiation, their communication, and all that kind of stuff that we'd done earlier in the course was revisited, which was nice. And then I said, okay, so I shared my screen and I put this graph up and I said, okay, so great, yeah, look, you know, that's the shape you all had on those nature tables. It looks right. And look, yeah, absolutely 0.8 is the maximum stationary point and 2.4 is. So are we all happy that the biggest value of that function is? And sure enough, some people went, well, what's happening over there? So yeah, the problem with the cubic function here is that it continues forever, increasing as we go to the right and decreasing forever as we go to the left. So we actually need to consider the endpoints. And so that was my kind of visual prompt to then lead in to writing up the note for this. But what I kept doing is coming back to this. So, I mean, we then talked about, well, what happens if we change the kind of the limits of that? You know, what values, what could we change the endpoints of our closed interval to be so that the maximum and minimum stationary points would be the, in fact, maximum minimum values in that interval. And this was so easy. You can see I just typed in 3 very basic functions there, the function that was given in the question and the vertical lines that match the endpoints. That's all I put in. And it meant I could really quickly and easily do this. And what I would encourage my higher class to do is that every time they worked on the exercise, and I was using Heinemann maths, I think, kind of pathetic, I know this, but I think I'm right in saying it was exercise 6.0 in Heinemann higher maths, I think, is the closed interval exercise. And what I said is, look, you know, just sketch it in DESMOS every time and check your answer. Don't be going to the back of the book. Just type the 2 vertical lines in, the x coordinates of the endpoints, type the function in, and that's how you check your answer. And just that way, they're never going away from the graph. You know, it never just becomes a page of algebra and calculations. They know to think of it this way. Now, I know that when it comes to exam time or final assessment or, you know, whatever we're going to call it this year, the pupils won't have access to DESMOS. But what I want is them to have a brain that associates the algebra with the graph, with the geometry, so that when they come across that question, they really understand why they have to check the endpoints. It's not just when it's a closed interval, you check the endpoints. And hopefully kind of using this backs that up a wee bit. This one of the pupils in my higher class asked and got in touch about a homework question. The homework question was given as, here's the equation of a circle, here's the equation of a line, technically a set of lines, for what value of k is it a tangent? And the pupil was just saying to me, I just don't understand what k is here. I don't understand what the question is. I think it was a really good question. They weren't just saying, I don't know how to do it. They were saying they didn't understand. So again, it took no time at all just to type those 2 functions in, and I put this in and said, go to that and hit play on k. It took me just 2 minutes to do that. I sent them to him and said, look, you'll see that there are values of k for which the line meets the circle at 2 points, so as a curve, that there are values of k for which the circle, the line misses the circle completely, and there is at least one value of k for which it's a tangent. And I deliberately actually set it between 0 and 10, so that he would then ask when he solved the question why he had 2 values of k, because of course he then, when he solved the question, found the value was k is 7 that made it a tangent. But he's like, but I have another one. It's just like, yes. So actually I've cheated a wee bit. I've kind of hidden it from you. So let's change it here to get the other value. And then sure enough, that then matched with the algebra. But what I liked about this was that it showed that changing k changed the line, and so that changed the scenario. So then a question like that, which values of k work, actually makes sense geometrically as well as algebraically to the pupils. So I thought that was quite a nice one, and then shared it with the class in the discussion, said, look, JK, I'm not meant to use people's names, asked this question, so this is what we've done and this is what it means. And I think, showing them that type of thing as often as possible really helps them to then be confident about it and understand it better. What was another one I did? So one time I redug this one out when I was teaching parabolae in kind of factorized form. I kind of threw this together, just kind of showing kids, how that works. So when you're working on teaching factorization to a National 5 class, what's the purpose? Showing them how it relates to the graph. Maybe, you save this for when you're doing relationships and solving using the graphical method, but showing them that, one thing I found when this kind of came in at National 5 is people kept wanting to multiply this out and then refactorize it to solve. So the kind of real purpose of this graph that I had with the class was to show them not to kind of bother if they want it if they want to get the roots. And then I did do a slightly extended version of that for the more general one, when we've got kind of more non-unitary coefficients of x in our factors there. And so they were able to kind of see the connection, how you can have 2 points of intersection. Obviously, these ones always have at least 2 or 1 because of the way I've constructed the equation up there. And that's kind of how it works. I mean, around that time, what I really want to show you now is kind of how to create your own. So let's say I was going to kind of create a new one. So if I take a new blank graph, and let's say I was maybe doing a bit of work on that big chapter, the kind of the big thing at National 5 that you maybe do near the end of the year on quadratic theory, when you kind of teach all your parabolae and you teach your kind of, what complete square form looks like as a graph. And the kids are kind of maybe struggling, I find often in National 5, they really struggle with the kind of graph part of the parabola, but they tend to be quite good at the solving part because they've maybe mastered factorizing earlier in the course. So that's something, okay, well, I know how to factorize. So actually just that extra bit of setting each factor equal to 0, that's okay for solving. And generally quadratic formula, they seem to cope quite well with, because as long as they can identify A, B, and C, they're quite confident about substituting into that formula. And so they're quite good at the discriminant stuff. Generally speaking, I find they're kind of better at the algebra side of it than they are at the graphical side of it. So what I'll often do with a National 5 class then is then present it to them and think about it in terms of the quadratic formula. So we just make our kind of standard quadratic like so, x plus c. We can put all of those in. I mean, the first thing I would probably do here is animate A and talk about what happens as we change the values of A. And so straight away, I can kind of probably reinforce that idea that I've taught them, that obviously to be a quadratic, A can't be 0, because then we have a straight line. To be a quadratic, A needs to be non-zero. And then, of course, what shape do we get when A is positive? What shape do we get when A is negative? So I can kind of reinforce that really quite quickly in the graphs. And then what I might show here is, well, what happens when I change the values of B? Okay, not much. What happens when I change the values of C? Okay. What if I change a few of them at once? What does that start looking like? What do all these different parabolae look like? And I might kind of lock them somewhere. And then I might say, well, okay, what if we consider the value of, oops, why is it not letting me type that in? it is b squared minus 4ac. So let's say we've taught the discriminant now. Let's look at that and let's change the values. Oh, what happened there? Okay, so the discriminant is negative, no real roots. Well, that's what that actually looks like. Okay, and if I change the value of b here, I can get it up to being positive, and again, 2 distinct roots. And it's just a really quick, easy way to do that. It's reinforcing kind of what they know. They're used to calculating the discriminant. I hope they're kind of confident on that. Generally, I've found National 5 classes are quite competent at calculating the discriminant. But what they tend to have is this kind of parrot fashion, maybe about the 3 cases, but just having it next to a graph every single time. And, you know, we can then just change this for particular questions. Like, okay, we don't need A, B, and C. The question in our textbook was 3x squared plus 2x minus 5. We just type it in. We can see it's got 2 distinct roots, and actually we can check that when we evaluated the discriminant, that is what we got. And because it's greater than 0, we get that. And that's really kind of all I do. The only thing I want to show you how to do is when you make these, you just hit save. You can, well, you name it up here. So I might say, you know, this is my quadratic formula task. Actually, do you know what? I'm going to not save it the way I've done it. I want to put A, B, and C back, because what I might do is send it to them in that form and get them to kind of play about with the values of A, B, and C. But if I save it like that, so I could call this, you know, quad formula graph. Save it like that. That's it done. And all I need to do to save that graph with you guys, and all you would need to do to share it with your class, is to copy and paste the URL. And that's now a resource you have for every year if you want to refer to it. It's saved in your library in DESMOS. It'll be at the top of mine, quadratic formula graph. I can get that if I thought it was good. I can save it share it with the class any year from now on. I could share it with other classes right now, and pupils can just access it by clicking on that link themselves and kind of exploring. It's quite easy to share things that way, to share it with other teachers. And I would just, I find it quite quick and easy to do that. And I would like you to have a go. So with the remaining time in our session, which isn't much, I've talked too much. Apologies, folks. What I was going to get you to do, and there maybe won't be a lot of time for this, so what I'll get you to do instead is have a go at it yourself in your own time. Apologies for that. Is to find or adapt a graph that would help with the teaching of some of this. So you kind of saw my attempt at this with the kind of factorized form graph that I created. But this is some of the stuff I find pupils find hardest in National 5 Maths. What I was going to encourage you to do was to kind of go into groups. But gosh, time got away from me. That's so embarrassing as a teacher. You know, you should have your timings all figured out. So yeah, I apologise you didn't get a chance to discuss. I was hoping to make it more interactive initially, but then when I saw the size, I realised I couldn't do it the way I wanted to. Okay. So you're not going to be able to do it in your breakout rooms the way I thought, because by the time I put you in breakout rooms, it'll be time to go. But if you would like to spend a little time at the start of your lunch doing this, or sometime in the future, have a go, just go in, create something, or find something in the actual library and send it in. If you're able to do it just now, stick it in the chat. If you're not able to do it just now, send it to me on Twitter, you know, and I'll maybe kind of collate all of these. I've been Neil Tilston. I'm really sorry, folks. That's terrible. I wasn't keeping an eye on the time. The problem is the clock on mine disappears when I share my screen on my laptop. I'm so sorry. I'll put the slides up. What I will do, if people sort of send me these in, I'll add an extra page to this slide and I'll put the links to what people send in for quadratics. And I'll share it out on Twitter as well. So hopefully if people kind of send stuff in, I can get it that way. Oh dear, how embarrassing. I'll have a quick look at the chat and see if I spot anything anyone said. Sorry. Yeah, okay. I'm glad people have found it useful. I'm sorry it wasn't a discussion though, because it was advertised as a discussion and I just didn't get time to do that with you. I'm sorry, folks. It's good. But yeah, I'll keep an eye out. If you find anything or you come up with anything, please send it to me either on Twitter and I'll share it. Or stick it in the chat there. Okay, that's good. It looks like some people have found some useful things in it anyway. So yeah, apologies. I don't want to run into your lunch, so I will stop talking now. Thanks for your attention, folks.
thanks very much, Neil. That was a really, really excellent talk. Loads of positivity in the chat. I think everyone's really enjoyed that and found it really helpful.
Yeah, I'm really sorry people didn't get a